Okay, so let's begin today's class. Today, we will start talking about the FET again. And once we cover that, I'm going to take your questions, if any. Okay, so basically, what we have done is we have talked so much so far about the JFET. And in this course, we'll only talk about the JFET. There are other kinds of field effect transistors like the MOSFET and the MESFET that I talked about in the very first introductory class on field effect transistors. However, we are not going to describe them in great detail simply because we don't have the time, because we still have digital electronics to cover in the 2 weeks that's left, and oscillators, which is coming this week. So we will stick to JFETs, but the basic structure of the theory is more or less the same in all cases. So far, we have seen how a JFET works, what its construction is like, and then its operation. And we have also talked about biasing of JFET circuits. Today, we will sort of complete that, in a sense, by talking about the AC behavior. So far, we have talked about JFET amplifier circuits, how to bias them, and so on. But an amplifier, of course, is used to amplify signals. So today, we are going to look at small signal AC amplifiers. Once again, let me remind you that we are using this qualifier small signals basically because what we are saying is that the DC biasing sets up quiescent currents and voltages in the circuit. And when a signal comes in, you have fluctuations about that quiescent point. When you say the signal is small, what you are implying is that you can linearize the problem about the bias point, basically do a Taylor series expansion and keep only the first order terms. And this is this linearized version that we are talking about. Actual amplifiers, of course, may not always be small signal. Signals may be large in an actual amplifier. And of course, if a signal is large in an actual amplifier, what happens is that your linear approximation is no longer perfectly accurate. Then you have to take into account higher order terms. And by the way, taking into higher order nonlinear terms might lead to some very rather unexpected behavior. You might end up with say, typical nonlinear behavior like bifurcations or chaos, but that is for a more advanced subject. In fact, when you go on to study nonlinear dynamics, you will see electronic circuits, especially electronic circuits in the nonlinear regime, playing a huge role there, at least for verification and say actual experimental realization of many of the theories that you find in nonlinear dynamics. But we are not going to talk about those things. We are talking about small signal AC amplifiers, linear approximation. We have already done this with the BJT, and you will find that with the FETs, things are actually much simpler. Much simpler because of basically two things. One, a FET is voltage controlled, and the other thing is related. A FET has a huge input impedance. Remember the PN junction, the gate, which is the input in these. So when we say small signal AC amplifiers, we will stick to the common source version, where the gate is the input and the drain is where you take the output from, and the source is effectively grounded. Now, the gate to channel connection is reverse biased in a JFET. In fact, in a MOSFET, there is a layer of insulator between a metal oxide. That's where the name, that's where those letters MO in MOSFET come from. So you have an oxide layer, which is actually an insulator between the gate and the channel there. So there, this is even better. The input impedance is, for a MOSFET, is even higher than a JFET. The input impedance in JFET is high simply because you're talking about a reverse biased PN junction there. So basically, very little current flows into the JFET, rendering it any JFET circuit as a circuit with very high input impedance, at least from the JFET itself. Remember, the amplifier, of course, has other connections besides the JFET. And when you talk of input impedance of the amplifier, You will say how much the source sees. That may be due to other components. We will soon see that. So let's start the analysis. But before we do that, we have to talk of a small signal model of the JFET. That is, what does this JFET behave like when you just consider the fluctuations? Here you have a drain, source, and a gate. And the very first thing that you realize is that is exactly what I said right now. For the field effect transistor, the Zi for the FET is very, very high. We are going to consider that to be infinitely high. Okay, so that much is straightforward. Now, what about the output? On the output side, we have this relation for ID. Remember, this is the total current in the drain. So that's not the signal. This is actually the DC value plus the signal. That's given by, at least approximately, by this very famous formula that we have been seeing so far. Now, when you talk of small fluctuations, basically the input VGS fluctuates a bit and ID as a result fluctuates. So we are worried about this quantity. How much does ID vary in response to VGS's variation? And this quantity in front, what will the dimension of this factor here be? And remember, we are just saying delta ID is delta VGS into something because what we are doing is we are just keeping the linear term. Delta ID would be delta VGS into something plus delta VGS whole square into something, etc., etc. Again, Taylor series. We are just keeping the linear term in the Taylor series. So what should the dimensions of this quantity here be? Anybody?
Admittance.
Yeah, it should actually be admittance, that of admittance, because it's current by voltage. However, this is really not an admittance, simply because admittance would mean voltage somewhere causing a current there. Here, the voltage is between the gate and the source and is causing a current in the drain. So, although the dimensions are those of the admittance, this is really a different kind of object, but it's called GM. M stands for basically mutual. It's an admittance, it's a mutual admittance, it's sort of how the input voltage affects the output current. Okay. And frankly, GM is given by this quantity. But in most cases, what we will do is we will pretend that VGS changes slightly enough that replacing this with the partial derivative is not going to be too bad an approximation. Okay. So you expect the change in the output current to be this quantity GM into delta VGS, and GM is given by this partial derivative, of course, evaluated at the DC value of the current, at the quiescent point. Okay? Of course, when the quiescent point changes, since the relationship between ID and VGS is nonlinear, as you can see here, when the quiescent point changes, so does GM. But for a particular quiescent point, GM has a particular fixed value. And when you move slightly away from that quiescent point, the change in the current is just given by that GM into delta VGS. In fact, calculating GM is rather trivial, at least from this formula. You can see GM works out to be minus 2 IDSS by VP, this quantity, when you into 1 minus VGS by VP whole square. Sorry, 1 minus VGS by VP. Right? That's just differentiating this expression, nothing else. And note that minus 2 IDSS by VP is a positive quantity. VP, the pinch of voltage, is negative. And this is what you call GM0, simply because that's what GM is going to be when VGS is 0, because the formula is 1 minus VGS by VP. So with the gate shorted to the source, the mutual admittance, or also called the transconductance. This is the formal name for this, is often the transconductance. Admittance and conductance basically mean the same thing. And trans simply because it's a transferred conductance. It's from one place to another. Voltage here causing a current there. So So this is the formula that you get. Or very often people write this in this form, GM0 is 1 minus VGS by VP is simply square root of ID by IDSS. So depending on whether you are focusing on the current ID or you are focusing on the voltage VGS, you use either this formula or this formula to find out what GM is going to be. These are of course quiescent point values. When you say VGS, you put in the quiescent point value of VGS, etc. The same here, the quiescent current ID. So this is really square root of IDQ by IDSS times this quantity GM0, which is nothing but twice IDSS by magnitude of VP, which is of course this factored in front. Remember, VP is negative, so mod VP is minus VP. So everything falls in place. So is this okay so far? Yes? Any problems with this? Okay, when you're saying mum, I'm assuming that this is sort of easy to understand. So the next question is, how would you actually model this in a circuit? So first of all, Zi goes to infinity. So you have the gate, you have this gate thing here. And how do you model an infinite impedance? You have the source here, down here. So this entire line will be connected to the source. So you want an infinite impedance. How would you model that?
By a break in the circuit.
By a? Sorry.
Break in the circuit.
By a what? Break in the circuit. Right. Or by connecting nothing here. That's it. So this is how the FED is modeled. The gate is isolated from the source. This is, of course, only for the small signal approximation. When we are talking about DC, we are not going to, of course, do that. But for AC, even for DC, of course, because it's reverse bias, we often assume that there is a open circuit between the gate and the source. But the basic idea is for AC analysis, the gate, in the small signal model, by the way, this is just like the H parameter model that we use for the BJT, or the simplified H parameter model, or other models that we use for the BJT. We're trying to do the same thing for a FET. And you will find for the FET, things are much, much easier. On the other hand, between the drain and the source, what do you want? You want this relationship to work. Or this, of course, is small ID. The AC value, AC current will be GM VGS. Remember, we use small letters to denote fluctuations. The small ID is actually delta ID. So this, and VGS, small VGS is delta VGS. So this is the relationship that I want to show. So this is your ID. And ID has to be GM times VGS. So how would you model that? Yes? If you remember your H parameters at all, you should be able to say this very easily. H parameters, H, Z, Y. We did this all the time. We essentially had a Taylor series expansion, and then we tried to make a circuit out of it. So what kind of circuit component will give you a current ID, which is GM times VGS? VGS, remember, is the voltage here.
A voltage control current source.
Right. Now, I'm not very sure whether everybody is following this, so let me just explain this in a way. One way to get a current out of a voltage is to put an admittance in the path. Okay, we usually just put a resistance in the path and just use 1 by the resistance to find current out of voltage. However, that will give you a current between the terminals across which the voltage is. Here on the other hand, the voltage is here between gate and the source, and you want a current here between the drain and the source. That you cannot get by using an admittance. An admittance is local. Ohm's law, and this is very important, and this is where most people make mistakes when they use Ohm's law. Ohm's law sounds very simple, but very often most students and even teachers make mistakes when they apply Ohm's law simply because they forget this very basic fact. Current between two terminals is proportional to the voltage across those very two terminals, not somewhere else. That is Ohm's law. And that actually tells us that you cannot use an admittance and use Ohm's law to get this. The only way to get this would be simply to say that there is a current source which is driven or which is proportional to this gate source. There is a controlled voltage source. Now, this is something which you have seen throughout in the Z, Y, and H parameter models. Whenever you have a current somewhere which is controlled by voltage somewhere, or a voltage somewhere which is controlled by current source, current somewhere else, you would need a control source. So this would be my very first model for a FET, a very, very simple model. No connection between gate and source, and a controlled current source, GM/VGS, between the drain and the source. That's it. And frankly, this is almost adequate for most circuit analysis. Indeed, if you looked at this equation, you would say not only is this adequate, this is all you can really do. At a linear level, this is exactly what this is. Notice that ID could have depended on VGS, and as well as could have depended on VDS, right? ID is the current through the drain. But remember when we talked about the FET characteristics, ID does depend on VDS in the linear ohmic region, but after that, it flattens out and flattens out to a formula which is given by this. This, of course, is the formula once pinch off has occurred. So once ID is saturated. So this is the kind of behavior you get. But I've deliberately drawn these lines. Okay, it was more because of my poor drawing skills, but I can now claim legitimately that, at least after the fact, that I've deliberately drawn these lines to have a slight upward slope. And that upward slope would really tell you that ID actually is also dependent on VDS, even in the pinch-off region. So in the pinch-off region, the major dependence is that due to VGS. This is for 1 VGS, say 0 volts. This is for VGS equal to, say, minus 2 volts or something. So ID depends drastically on VGS, but very, very slightly on VDS. So basically, this equation requires a bit of a modification. ID is GM/VGS, but it also depends on the drain to source voltage. This small VDS is a change in the drain to source voltage. And this characteristic is showing you that if the VDS changes, so this is your delta VDS, there is a small change in ID. Okay. And once again, when we are doing the linear approximation, what I should put in here is a constant which of course depends on the Quiescent point. So what should the dimensions of that constant be? What should the dimensions of this constant be?
It should be an admittance.
That could be an admittance, right? This is a current which is a sum of two currents now. Yeah, it has to be an admittance, right? Well, we are not that comfortable dealing with admittances, so we will write that as reciprocal of resistance. This is called the diode. Sorry, not the diode. My mistake. This D here is not the diode, D here is drain. This is called the drain resistance. So 1 by RD is just an additional term. 1 by RD VDS is a term that you will have in addition to GM VGS. By the way, should RD be big or small from what I've said so far about the characteristic curve? You can see that when VDS changes a lot, ID changes only very slightly. In fact, this formula would have told you that ID doesn't change at all if you change VDS. There is no VDS in this equation. However, this equation is not exact, so there is an additional dependence on VDS, which is very slight. So is RD big or small? What is RD? RD is basically delta VGS by delta ID, right? Is that big or small? Or you can replace it by the partial derivative. Should this be big or should this be small? That should be obvious from this picture. And frankly, the fact that everybody else in this class stays quiet is a bit worrying. I'm not very sure whether I'm at all getting through to anybody else.
Sir, RD should be big.
Yeah, this should be big because VDS has to change a lot to get a small ID change, right? So delta VDS by delta ID has to be a large quantity. And this RD is small, and that should be also easy to understand. Remember, our first approximation was just this. You didn't even have this term. So if this is a good first approximation, as I said, this term had better be very small, which means RD should be very large. So small RD is a very large quantity, and very often 1 by RD is so tiny compared to GM. That is, this term is very small compared to this term, and we can ignore this. So this model that we have, which only has GM VGS for ID, is a pretty good model often. But if you want it to be more accurate, you'll have to incorporate this other term. So how do you incorporate this other term? Now there are two terms here, two currents adding up to a current. So when you add two currents, when do you add two currents? When are currents added? Whether circuit components are in series or in parallel?
Parallel.
I think people have completely forgotten their initial classes.
Parallel.
Or this is class 10 actually. Yeah. Yes. When are currents added?
Parallel.
Yeah, when branches are parallel. Okay. So when you have two branches in parallel, am I still connected? Because I had a signal come to me a while ago.
Yes, sir, you are connected.
Yeah, I'm connected. Okay, good. So you need two branches which are in parallel, and the other branch is actually just a genuine resistance, right? Because VDS is the voltage between these 2 points, and you are saying that the other branch is going to carry a current of VDS by RD, so that the total current coming in will be a sum of these two. So this is just modeled by resistance RD. By the way, sometimes you code the parameter as the resistance, sometimes you code it as the admittance. So you may also talk about YD. YD is of course reciprocal of this RD, delta ID by delta VDS, which is a very tiny quantity. Okay, so this is the small signal effective circuit. In fact, a very similar circuit, almost identical circuit, would work for MOSFETs and MESFETs as well. The basic idea is the gate to source is open, and the drain to source side, there is a voltage controlled current source in parallel with RD, which you can think of as think of just as this being a, well, imperfect voltage controlled current source with an output admittance given by, with its internal admittance given by 1 by RD. And remember, every current source, every real current source comes with an ideal current source in parallel with an admittance. That's exactly what this side is. As I said, this equivalent circuit is way simpler than the corresponding equivalent circuit for a BJT, because on the BJT for the BJT you have to worry about both the input side and the output side, right? On the input side, you have this HIE and HREVCE if you are using common emitter and small signal H parameter model. Now, HREVC can be ignored very often because that's tiny very often, but you still have an HIE admittance, HIE resistance to worry about on the input side between the base and the emitter. And on the output side, you have this HFE IB in parallel with 1 over HOE, or in parallel with the admittance HOE. Very similar to this, except for a major difference. Here, the current source is voltage controlled. In the BJT, the current source that you use, HFE IB, is current controlled. But that's easy to understand. A BJT is essentially a current controlled device. The effect, on the other hand, is a voltage controlled device. So this small signal equivalent actually makes life rather easy. In fact, it's very easy to deal with FETs, much easier to actually analyze FET amplifiers than BJT amplifiers, at least comparatively. So wherever you see the FET in a small signal model, you can replace the FET with this. And very often you can even make life even easier for you, just drop the RD. Because RD is usually too big to really matter. Okay, so let's see this in action in some circuits. So the first FET circuit that we are going to talk about is a fixed bias amplifier. We have already talked about its biasing in the last discussion class. And let me just remind you what the circuit looks like. The actual circuit looks essentially like this. Then you have an RG and a VGG. This VGG is required to make the, remember the source here is shorter to the ground. This VGG is required to make the gate go below the source, and hence you will have the gate channel PN junction. And then you have this. Okay, by the way, I'm not sure whether everybody understands this. Sometimes we draw capacitors like this, and sometimes we draw them like this. What's the difference? I'm sure many of you have seen this, right? Capacitors are either drawn with two parallel lines or with one straight line, one curved line. So what's the difference between the two? Okay, somebody was saying something, but I couldn't really hear.
The first type for DC and second AC. If there is AC component, then we use the second capacitor.
AC, and the other one is?
And there is only
But that's actually not really correct, because in this circuit, for example, you have both AC and DC. It's not AC and DC which is really important. Yes?
Sir?
Okay, somebody's writing something in the chat. Polarization. Yeah, Swapnil, you are right. It's polarization, or the construction is different in the two cases. Mostly these are electrolytic capacitors, and there the polarity matters. It's not really polarization so much, it's more polarity. That is, as far as DC is concerned, when you are setting this up for DC, you have to make sure that the polarity is just right, otherwise the capacitor simply will not work. And here, in the straight and curved line simply means the straight line should be connected to the positive side of the DC, and this should go to the negative side. So remember, VDD is positive on this case, so you are blocking it, and on this side you will have a load which is connected to the ground. So you will connect the, if you are using an electrolytic capacitor or any capacitor for which polarity matters, the plus end goes towards VDD. So this goes here. Similarly, this side is positive as far as DC is concerned. On this side, you will have a signal, but the signal is supposed to be a pure AC, should not have DC in it. It definitely should not have DC which sort of goes above the gate voltage. So this is what you should connect it like. So which line is curved, which line is flat matters. Okay, it's not as if you could just randomly write a curved line on any side. Okay, so the last day we talked about the biasing of this circuit. Basically, we said that the source is always at 0 volts for the biasing, the DC part. The gate is actually at minus VGG because of this VGG connected in reverse. And so VGS, the gate to source voltage for DC, is minus VGG. So that's a fixed value, fixed bias. You plug this in the ID equal to IDSS into 1 minus VGS by VP whole square relationship, or draw a graph. Either way, you find out exactly what ID is at the quiescent point is going to be. And VDD minus IDRD. ID, remember, is the current flowing here. So when you subtract from that, from VDD IDRD, you get the voltage at the drain, or which is also the VDS, VS being 0. So that's how you calculate the quiescent point or the bias point for this particular FET amplifier. Not a great biasing circuit, as we saw, simply because if you were to change your FET or your FET becomes older, the bias point drifts a lot in this circuit, which is not a desired property. But it is also one of the simplest FET circuits to set up and analyze. And now we are going to take a look at what happens when we start with this circuit and do a small signal analysis, AC analysis. Okay, the whole idea, I see from some questions that I get, people are still a bit confused, or people may have forgotten about what AC analysis really means. Your voltages and currents are actually sums of the DC value plus the AC values which come in because of the signals. The DC value or the average value we have already analyzed. That's our biasing analysis. The AC value is a fluctuation around that, and at least when we are dealing with a linearized version of this circuit, that is, we are dealing with a tailored series with the first order only, then we are within our rights to use something called superposition principle. So superposition principle is a standard metric which we often use in circuit analysis, but you have to remember that it can be used, strictly speaking, only for linear circuits. So frankly, the only reason you can use superposition principle here is because you are actually just using a linearized approximation, which is a very decent approximation, by the way. Just because it's an approximation, you should not necessarily consider it to be a bad thing. And as I keep on stressing, electronics, and in fact all of physics, is all about doing controlled approximations. Exact calculations are frankly rather useless, except to sort of write in an exam, or, okay, that's really not true. I spend most of my working life, that is my research life, trying to find exact solutions. So they have other utilities, but they are really rather rare. You know, that is one of the reasons why researchers tried so hard to find them, because they are rare and because they give good indications about the way approximate solutions should behave. But approximate solutions are all you really should do, or at least mostly do, in physics, and electronics, of course, is one place where you do them from the very beginning. So the linear approximation, once you have done that, you can treat this with superposition. And superposition principle simply says this: if you have multiple sources in your circuit, then when you can analyze them one after the other. But when you analyze one of the sources, that is, you can find out the currents and voltages due to one source first, then do it for another, then do it for another, and finally add up all your results. When you are doing it for one source, what we are going to do is replace the other source by its internal impedance. This is very, very important. That means if it's an ideal voltage source, you replace it with a short. If it's an ideal current source, you replace it with an open circuit. If it is a non-ideal voltage source, you replace it by its internal resistance. If it's a non-ideal current source, you replace it by its internal admittance. So this is what you are supposed to do. Okay. I just lost contact. I hope I'm no. Am I?
Yes, sir, you are showing.
Yeah, I'm back then. Okay, so I lost not only contact, my presentation is stopped. So let me start that again. And can anybody tell me what you heard when I last was audible? Yes?
Uh,
What was I saying? Or was everybody asleep? I do remember that I was in another long, well, detour onto why electronics gives you approximations from the beginning. But how much of the superposition principle thing did you hear?
Sir, you were explaining the limitations of that superposition principle. After that, we lost your connection.
Okay. Well, limitations meaning I was talking about whether you can use it for only for linear circuits, right?
Yes, sir. Yes, sir.
Okay. So, okay, but okay, in any case, even if it's a repeat, I talked a bit after that. Some of it may have already been said, but you will have to listen to it again anyway. I said that when you are going to use the superposition, so first of all, we are going to assume that we can use the superposition principle here simply because we have assumed the linear approximation to be valid. And then when you do superposition in any circuit, you have multiple sources. You are supposed to calculate one source at a time. Take one source, calculate the voltages and currents due to that. Then take another source, calculate voltages and currents everywhere due to that. And then add up corresponding voltages and corresponding currents. Well, once you're done with working it out for every source. But when you are taking one source, what do you do with the others? The answer is, when you're considering one source, all the other sources, not the control sources, but all the other fixed sources should be replaced by their internal impedance. So that is how it works. When you say internal impedance, you have to be careful. If it is the ideal voltage source, its internal impedance is 0. So it has to be replaced by a short. If it is non-ideal, it has to be replaced by its internal resistance. If it's an ideal current source, then its internal impedance is infinity. And it has to be replaced by an open circuit. No current flows, that's it. And if it is a non-ideal current source, it has to be replaced by its internal admittance, which is usually a very tiny admittance or a huge resistance. So that's how it goes. So when we were dealing with the DC part, we actually had the advantage that the capacitors here, these two capacitors, C1 and C2, blocked the DC from coming in, or more importantly, blocked the DC here from flowing out. So you could simply forget about this part and this part. You could just concentrate on this. But now that you are dealing with the AC, that is what happens because of the VI. Then what you have to do is, first of all, if you assume that the AC is high enough frequency, which we will do for simplicity, you can replace the capacitors C1 and C2 by shorts. So we have gone into a high enough frequency regime that the capacitors can be replaced by shorts, but not to such a high frequency that the, say, capacitance here between the gate and the channel. Remember, the gate and the channel basically has a highly conducting region, the gate P, another high conducting region, the N, the channel, separated by a depletion region which has no charge carriers. So it's basically like an insulator between two conductors, exactly what a capacitor is. So any reverse bias PN junction would actually have substantial some capacitance, but this capacitance will be tiny. So we are saying that the frequency that we are dealing with is large enough that we can treat these capacitors as shorts while not worrying about the other capacitors in the circuit at all. They're too tiny to other capacitors, meaning not capacitors you can see in the circuit, but other capacitors that are there between wires, that are there between the gate and the channel. These are stray capacitors or parasitic capacitors which come in the circuit. We are not going to frequencies which are so high that they will be effective. They will essentially have infinite impedance in this case, so we will just ignore them. So firstly, you have VI. So this is the AC equivalent, that AC equivalent circuit that I'm drawing here. Firstly, you have VI, the capacitor is shorted. Here you have RG. And then VGG has to be replaced by internal impedance. Now, a real battery does not really have zero internal impedance, but it has a tiny internal impedance, something of the order of ohms. So RG is anyway mega ohm order. So let's not worry about its internal impedance. We will just replace it by, oops. Okay, am I still connected? Because
Yes, sir, you are connected.
yeah, because it told me I lost my connection, but I'm back, I guess. So this battery can be replaced by its internal impedance, but frankly, you can simply safely ignore it because that's going to be very tiny compared to RG. RG we will keep at pretty large, somewhere of the order of mega ohm or so. So you can just replace it by a short. Okay, so that's for this side. And now I'm not replacing the FET by its equivalent circuit yet. So I will still keep the FET drawn in the circuit. I'm just showing you how the AC part works. Here, this is grounded. Now here, okay, this may not be a good idea to draw it as a straight line. You can, but let's. So this output VO is joined here by a short because the capacitor has been shorted. Now what happens to the RD? RD is joined between this point and VDD. But VDD has to be replaced by its internal impedance, which is 0. Because there again, assuming an ideal source. So what will happen to RD? Where is RD connected? Between this point here, which is anywhere on this line, right? And what? What is it? What is the other end connected to? This end. In the actual circuit, it's connected to VDD, but when you're doing an AC analysis, what is this connected to? VDD is actually shorted to the ground.
Ground.
So RD is connected between this point and the ground. So if anybody has any confusions about this, this is something you do everywhere. Or in PETs, in BJTs, every small signal analysis essentially works this way. So of course, in BJTs, that would be RC, but same idea. So is everybody sure about this? Does anybody have any confusion as to why RD is connected to the ground? No, if you are sure, then of course you don't have to say yes. I'm really asking people who are silent at this stage, if anybody has a confusion, please let me know. If you don't let me know, I'm assuming everybody has understood this. Okay, fine. So you have, this is your AC equivalent version of this, where we are going to just do the AC analysis, the signal, input signal, output signal analysis, forgetting about the DC part completely. And then the next, okay, but notice one thing. In the last class also, I talked about RG. Remember, as far as biasing was concerned, RG played no role whatsoever because there was no current in this branch, so there was no drop across RG. So whether you replace RG by a short or not made no difference, right? Now you see why RG makes a huge difference. Because for the AC signal, RG is all you have between this point, the gate, and the ground. If this had been a short, I said that last day also, but let me just repeat it again. If you had not had RG in the circuit, saying that, okay, RG doesn't matter for the biasing, why put it? But if you did not have RG, the signal would have been directly shorted to the ground. So if you connected a source here with source here Vs, that would first of all deliver a huge amount of current because you have a short to the ground. Even if that does not destroy your source, which it might, which it very well might, it would still drive such a huge current that all the source voltage would be that on the source's own impedance, which would mean that you will get no voltage here. And if you get no voltage at Vi, of course you get zero. So RG is essential for the amplification part, not for the biasing part. But you must have RG. And it's very easy to see what the input impedance is going to be. The impedance which the source sees, looking at the input terminal here, how much will it be? What the source sees is a current. It can drive current, and the current can have two ways. It can flow through this to the ground or flow through this. And how much can flow through this? Almost nothing, right? Because that's a gate to channel reverse bias PN junction. In the effect, of course, in the effective circuit that we will draw soon, that will be obvious. But even without that, remember that there's a reverse biased PN junction here, which means almost no current will flow here. So all the current will flow through this. So Zi essentially, so Vs, the source, only sees RG across it. So that's Zi. So Zi, the input impedance for this circuit, will simply be RG. Okay? So why do you need a huge RG and not a short? Simply because if you don't take RG to be big, then your input impedance is going to be small, and if input impedance is small, then the source resistance will play a huge role in deciding how much your output is going to be. So changing the source even with the same input signal will make your circuit behave very differently, which is not what you want. So Zi is RG, and RG should be taken to be large. Now, how large is large? The answer is it should be so large that you can essentially considered to be infinitely large, or at least very many times larger than your source impedance, but you don't want to make it so large that it begins to sort of compete with in impedance with the reverse bias here. The reverse bias allows nanoampere order current to flow. You want current through RG to be larger, much larger than that, so that you can safely treat the gate channel to be infinite impedance. So RG of the order of a mega ohm is fine. Because for a typical input voltage, you will get microampere range current, which is still much, much bigger than the nanoampere range current that you will get between the gate and the channel, and then through that to the source. So we have not even started analyzing or replace. We have not even replaced the FET with its equivalent model. We still have figured out a lot about the circuit. At least we have figured out why RG is necessary. We said that in the last day, but now we can see it explicitly in the circuit. Also, roughly how large should RG be? Mega ohm is fine. Okay, I lost contact once again. But let's start. Yes. I hope you didn't miss much. Anyway, I've been repeating myself over the last few minutes. So everybody is clear about why Zi is RG and why RG should be is neatly of the order of 1 mega ohm or so. If anybody has any confusion, please speak up. And I'm still audible, right? Just wanted to make sure that I'm still connected properly.
Yes,
Yes,
sir, you
sir.
are audible.
Okay. So next step in the analysis would be to replace the FET here by its equivalent circuit. Now that would be very, very easy for this. You have VI, you have, okay, let me just move this a bit down. RG between the ground. This is the gate. How is it connected to the source? It's not connected to the source at all. That's it. So this is open in the equivalent circuit. And then you have GMVGS between the gate and the source. The source is grounded, so sorry, between the source. The source is grounded, so this is fine. And then you have, okay, let's put in small RD, which is also between drain and the source. So let me just connect it here. This is actually joined here, but when you write ground symbols, it just means all the grounds are joined. And then you have capital RD in the circuit, which is, so that's your equivalent small signal circuit with the FET replaced by its equivalent. Is this okay? Just to remind you, this is what the FET is, and its equivalent gate, drain, source. This equivalent circuit is given by gate is open, no connection with the source. So you have a wire going all the way just to show that in principle the gate could have been connected to the source, but that's there more to emphasize that the gate is not connected to the source at all. So there is an open circuit. Then you have this GMVGS, and then you have small RD. So that's your effective circuit. That's what we have used here. So this part is clear to everybody, I hope. that this circuit, when you replace with the equivalent circuit, you get this. Any confusions? I'm assuming that silence means that there is no confusion. But let's hope that the assumption is correct. So now we want to calculate the output voltage. And by the way, there are three major things to calculate here: Zi, Zo, and AV. Zi we have already seen. In fact, Zi is also obvious from this circuit. Just hold on, I'm getting a call. Okay, I'm back. And nobody has said among you that you couldn't understand this. I'm assuming everybody is okay with this. Well, Zi, this circuit makes it even more obvious that Zi is RG, because from this side you can only see RG, nothing else. This whole thing is disconnected from here. Well, VO, how much is it? VO is this voltage. So can anybody just tell me how much VO is going to be from this formula? From the circuit, sorry. It's absolutely trivial. If you just focus on this side, you should be able to, VO is the voltage here, means it's the voltage between this point and the ground. So the voltage across these resistances. How much is it going to be?
GM/VGS time RD parallel capital RD.
So what is being said is GM/VGS is the current flowing here, and it's flowing through these two resistances which are in parallel. And so the voltage drop across the two resistances, which is VO, has to be this. Is this correct? This is not correct, by the way. Can anybody see why this is not correct?
A minus sign should be included.
Yeah, there has to be a minus sign. There's no GM/VGS is flowing this way, right? So it's moving this way. That would actually have produced a voltage drop between this ground and the drain. What you want is the voltage drop between the drain and the ground. So there's a minus sign. That's simply a matter of the direction in which GM/VGS is flowing. Okay? So that's VO. What's VI? Or how do you relate VGS here to VI? That's important, because you'll really need VO by VI. Now, so what you need is how much is VGS in terms of VI, and how do you figure that out? VGS, of course, is the difference between the gate voltage and the source voltage. How much is the source voltage here? From this circuit, it should be obvious how much the source voltage is. Yes?
0.
Yeah, the source is connected to the ground. It has to be 0. So Vs is 0. What is Vg? The voltage here. Come on.
So VGI.
That's again obvious. How much is the voltage of the gate? Remember, Vg is Vi, right? Come on, these are just joined together. There's nothing else here. So VG is VI, VS is 0. So VGS is VI. So VO, which is minus GM VGS RD parallel RD, directly gives you VO by VI, this ratio, output to input voltage ratio of for this FET amplifier, the voltage gain of the FET amplifier, is simply minus GM and for most practical circuits, small RD would usually be much bigger than capital RD. Remember, small RD, the FET resistance is huge. There's a drain resistance of the FET. It's actually huge. So for most circuits, it's going to be approximately minus GM RD. So that's your voltage gain. The transconductance times the drain resistance with a minus sign. So what does the minus sign signify here? Yes, you have seen negative voltage gains before. In the most amplifiers that you have dealt with, not most, but the most common amplifiers, have got a negative voltage gain. So what does the negative? So the C amplifier is a negative voltage gain, for example. What does the negative sign actually signify?
Is required.
Well, if only one or two people answer that, I'm a bit confused as to whether the rest of the class has at all understood anything or whether they're just they've just outsourced the job of answering to one or two people. And let me just point out, I have some marks in my hand for internals. If you don't interact, you get none of those marks.
Sir, hello, am I audible?
Yeah. Yeah, you're
Sir,
audible.
does negative mean the output is inverted relative to the input?
Yeah, that's exactly what it means. Or actually, a more formal way of putting that would be the output is 180-degree out of phase.
Yes.
That is when the input reaches a maximum, the output reaches a minimum, sorry. Is 180-degree out of phase with the input. VO is 180-degree out of phase with VI. So when VI reaches a maximum, VO reaches a minimum, and the other way around. We saw the same thing happen in the BJT CE amplifier, because in a CE amplifier, when the input current went up, that happened when the input voltage went up, the output current IC went up. But if IC goes up, then the voltage at the, just hold on. Okay, so I'm back. So this minus sign is so for the BJT amplifier, input current going up means output current going up. And if IC goes up, the drop across RC goes up. That means the VCE, what is really the output, that goes down. A very similar thing happens here. Okay, so this AV calculation is straightforward. Here. Now, the only other thing that we need to calculate is ZO, and that's slightly trickier, the output admittance. So does anybody remember how you calculate output admittance for a circuit? I need space, so I'm just moving all this calculation down. So this is your circuit. You want to calculate its output admittance. How do you do that? That is, you want the admittance from this side. But just looking at the resistance that you get from this side will not be enough, because looking at voltage by current ratio, which is the resistance, is not enough. Simply because when you're looking at the output side, you don't just have ZO. Remember, the output has ZO, but it also has AVVI. So that's the effective output side of an amplifier. What we want is just to find out what ZO is, not and get rid of this AVVI part. So what is the easiest way of getting rid of AVVI?
By setting the input voltage 0.
And also adding a generating voltage at the output side.
By? Well, the
Also
output side
connecting
is
a generating.
no, yeah, that's later. But the first step is you get rid of AVVI simply by, this is a V, not an AO. Simply by putting VI equal to 0. Just make VI 0, then this shorts out, then you see only ZO. Of course, the problem is if you want the voltage by current at the output side, when VI is 0, the problem would be our voltage at the output and the current at the output would usually vanish. If there's no input, there should be no output. And therefore, this will not work unless, that's the second step that you talked about. You said VI equal to 0, then connect a Vx here, some voltage on the output side. Remember, this is just an effective circuit. It doesn't care whether what you have on this side. So you could also connect a voltage source here. So if you connected a voltage source on this side, let's say a Vx, some voltage source, and try to calculate the current Ix which flows in because of that, then Vx by Ix at Vi equal to 0 will give you 0. Okay, but in this case it's even easier, but still, let's go through the motions anyway. If you have made Vi equal to 0, how much is VGS then?
0.
To put Vi equal to 0, how much should VGS be?
0.
Vi equal to 0 immediately says Vg equal to how much?
0.
0, right? VGS joined to Vi. So Vg and Vi are equal anyway. And Vs is always 0 because it's grounded. So VGS is 0. So this particular current source is now 0. What that means is there is no current here. That means you can just forget about this. So now, I don't even have to go through connecting a Vx and finding out Ix. I can immediately write down what ZO is going to be, the impedance on this side. If you don't have this, what should the impedance be when seen from the output terminal? What does the output terminal actually see? It sees a
Parallel
resistance
connection
RD
of
in parallel with small rd, right? So it just sees this. And once again, small rd is much, much bigger than capital RD. So the output impedance in this circuit is approximately capital RD. So what this circuit, at least for the fixed bias circuit, the calculations are very, very straightforward. Okay. Zi, let me just repeat, Zi. We look at it from this side, it sees nothing, it just sees RG. So Zi is RG, nothing to be done. Z0 is simple because once you make Vi equal to 0, this current source simply drops out. Vg being always equal to Vi in this circuit and Vs being always zero. Vi equal to 0 means Vgs is 0, so no current here. So all you see is this. Of course, you could formally still connect a Vx to the output and measure and calculate what Ix is going to be and then find Vx by Ix. But it's obvious that what this voltage source is going to see is just these two parallel resistances. So you are going to get this. And AV, the only other calculation that we had done, for that you have to be, the only thing you have to be careful about really is that the current GMVGS. Now, of course, you are saying there is an input voltage, no voltage source connected to the output. So this GMVGS drives the current through this parallel combination. So this is the voltage drop, but you have to be careful about the sign. You get a minus sign. And since VGS equals VI, VO by VI just works out to be this. So pretty straightforward. So what we are going to do next is we are going to analyze another circuit which is slightly more complicated than this one. Remember in the last class also I said that the fixed bias circuit is not that great, that it has basic problems with stability. That is, any change, any fluctuation in the properties of the FET makes a huge difference. So what you could have is something like this. A self-bias circuit. And in the self-bias circuit, this is what you have, Vi on this side. Again, on this side, you just have Rg. You do not have a VGG any longer, simply because you do not need the VG. Here, since no current flows through this branch in DC, remember the current, there will be a current, but the current will be very, very tiny. And Rg, despite being rather large of the order of mega ohms, Rg times that nanoampere order current would still be tiny. So we can just say Vg is 0. But Vs here is not 0 because S is now here, not down here, right? So source is no longer connected to the ground. It's actually connected to the ground, but through a resistance Rs. And so Vs is going to be Rs times the current through the source, which is the same as the current through the drain. So what happens is there is a Vs which is proportional to ID. So Vs is actually IDRs. VGS, I'm talking about the DC part here, VGS is minus IDRs. So you have this sloping straight line instead of the vertical straight line of VGS being constant in the biasing circuit, which makes the fluctuations smaller. And then you take the output across this. And of course, what makes fluctuations smaller also reduces the gain. So very often what we do is we do not connect it just like this. We actually put a capacitance across this. Just like we put a capacitance across the RE in the self-biased circuit for a BJT. You have RE and CE there. Now here you have RS and CS. Okay. So what is the job of the CS? The job of the CS is to ensure that for bias, for the DC part, RS is very much in the circuit, it's producing stability. But on the AC part, the CS has a small enough input impedance that it just shorts out RS. So C1 gets shorted, C2 gets shorted, and this also gets shorted. Now, the AC equivalent, this will be, well, you have VI here, here I'm saying AC equivalent, I'm not replacing the FET with its equivalent circuit yet. So you'll have RG connected to the ground. This is the only change here is the capacitor has been shorted out. But now RS has been shorted out, so the source is connected directly to the ground. This is VO. No capacitor here, shorted out again. RD. Because VDD is shorted to the ground, comes between the source, the drain, and ground. Done. Now, can anybody tell me? I'm not even going to do anything more. I just want ZI, ZO, and AV. Can anybody tell me what they are going to be? No calculations needed actually. If you have paid attention, you should be able to tell me what this is. What these are.
Zeta is
Let me just go back to the previous circuit. Here you had RG and a VGG. You had a short here. In this circuit, you have RG which is directly connected to the ground, and you have RS here. If you look at the AC equivalent, there you had RG and VGG, but for the AC equivalent, you just had RG to the ground. And on this side, you had there you had a short. Here you still have a short, right? CSS is shorted out. Is that okay? Two are shorts in both circuits. RD is connected between the drain and the ground in both circuits as far as AC is concerned. In the fixed bias circuit, you have an RG in series with the VGG, but for the AC circuit, VGG is 0, so RG is directly connected to the ground. And the only difference here, RS, because of the capacitor CS and assuming that we are at a higher frequency, has been shorted out, so this is also not. So, what should these results be? I don't have to do any calculations again. This exact, the AC equivalent circuit to this one, the self-bias circuit, is exactly the same as the AC equivalent circuit for the fixed bias circuit, right? Notice this was the AC equivalent. RG connected between the gate and the ground. This was shorted anyway, and RD here between the drain and the ground. This circuit is exactly the same. Why? Because the only differences that we had were contributing to the DC biasing. Of course, you have stability and all, more stability and all that for the DC bias. But the rest of it is exactly the same. Is it okay with everybody?
small RD.
Any confusions? Just tell me that.
Sir, am I audible?
What? Small RD. Small RD, well, you don't have small RD in the circuit here simply because the FET is still in the circuit. Right? I've kept the FET in the circuit yet. I have not replaced FET by its equivalent circuit. That will come in the next step. I'm just looking at this circuit and seeing what its AC equivalent is going to be. Not the FET small signal equivalent. I'm just doing the AC analysis for this circuit. I have still kept the FET inside. Then I will replace the FET by its small signal equivalent circuit with GMVGS parallel to RD and so on. And then I will do the calculation all over again. But I don't have to do the calculation all over again. I've already done the calculation. The AC equivalent here for the self-bias circuit is exactly identical to the AC equivalent for the fixed bias circuit. The identical circuits of the same results. Is there any confusion about that? We did this analysis also in two steps. First, replace this circuit by the AC equivalent. In this, you don't see any RD or GM, simply because the FET is still in the circuit. GM, RD, these are properties of the FET. So they are very much there in the circuit, you just can't see them because they're hidden in the FET symbol. And then we replace the FET by its equivalent, that is this thing. And of course, not just this thing, also this. The gate is isolated. And then we did the analysis. Since doing the AC equivalent from here to here gives you exactly the same circuit for the AC equivalent as for the fixed bias, the results are also going to be exactly the same. Yeah. Is it clear why you don't see small RD in this circuit yet? You will. You will want to replace the FET by its effective equivalent circuit. Is this clear? Yes or no?
Yes, sir.
Well, when I say yes or no, I mean if it's not clear, please speak up. Okay, so there was nothing much new to be done here, but let's just say we did not bypass the source, RS. It might be that we could do it like this. Let's push this out. And of course, if the FET had not been bypassed, that is not trivial. And sometimes, sorry, not the FET, the source ratios had not been bypassed, then what would happen? And sometimes what we do is we don't bypass the entire. Okay, I was gone once again. So again, okay, I've now figured out why this is happening, because right now my wife is taking a class in another room. My son is attending a class in another room. So we have 3 meets going on at the same time. So that's why I'm having some difficulty with the connection right now. So I hope everybody can hear and see my screen as well. Yes?
Yes, sir.
Yes.
Okay. So I don't remember how much I said before I got lost because I did not know when I got disconnected. Did everybody see this thing about not bypassing the entire RS? That is,
No,
you
sir.
don't put a capacity. Mhm.
Last I saw, you just push the circuit down. That's it.
Okay. Not the circuit, the calculation, I guess. Okay. This I push this down, right? That's what you meant. Or was it even worse?
Yes, sir.
Okay. So the basic idea is that as long as the RS is completely bypassed, that is, you have a resistance RS here and a capacitor which completely bypasses this, then when the frequency is large enough, the capacitor is going to replace the RS by a short, and you will have no difference for the AC equivalent part between this circuit and the fixed bias circuit. So that would be easy. But suppose the RS is not bypassed. So here you have a self bias circuit with an unbypassed source resistance. Sometimes we do use such circuits, and sometimes what we do is we break up RS into two series resistances and bypass the larger part, but still leave some small RS in the circuit. So now the AC equivalent will have an RS connected between the source and the ground. It could be the entire source resistance if it is not bypassed at all, or if it's partially bypassed, then this instead of RS, you will have to take that part which has not been bypassed. When I say that, all I mean is instead of connecting this, you could have connected this. So this could have been connected here. That means no, not this part, but this part. That means that the capacitor essentially shorts out this part, but you still have some resistance left in the circuit, even in the AC part. So typically that's what is done very often, and you will get a source resistance here. Now things begin to get more interesting because the previous part was not a boring. You get the same result all over again. Now you need to replace this by the FET's equivalent. And what I'm going to do is I'm going to make life a bit easier for myself. I'm going to assume that small rd is much, much bigger than capital RS and capital RD, which the other two resistances on the output side, which is very often the case. So I'm going to ignore small rd for the time being. Small rd, remember, is in parallel with GMVGS. If small rd is huge, then just drop the parallel path. That makes the analysis a lot simpler. Of course, for a more accurate thing, you have to do the analysis with small rd in the circuit. That takes some more algebra, but the basic idea is still the same. So here I'm replaced. Okay, let me just use a different colored pen just to distinguish the thing. Here I have VI, RG, VG. Now I'm replacing this gate, drain source, this FET in between by its equivalent circuit. So what I'm going to do is put in GMVGS on this side. Not put in the RD simply because RD I'm assuming is too big. Too big to carry any substantial current, that is. You have capital RD here. That's your drain. Capital RD goes here. The major difference between this and the previous cases, this is where the source is. And the source is not grounded. This is the ground. There is a RS between the source and the ground. Simply because I have not bypassed the RS, or at least not bypassed the whole of the RS. So this is the difference. By the way, if you did not make this approximation, there would be small RD in the circuit. It would be like this. So this purple additional piece I'm ignoring. Is this equivalent circuit clear to everybody? This part is essentially this. But the source is no longer grounded, so the source has to be connected to the ground through the RS, not shorted. So that's it. So now what we need to do is calculate the ZI, ZO, and AV for this circuit. So how do you calculate ZI for this? So quickly, somebody tell me what the ZI is.
This time you have capital RD parallel with small rd plus capital RS.
Okay. Let me point out one thing. From this side, I'm not disagreeing with
Oh,
what you are
sorry,
saying, except
I
that
actually
I can't
said
see that easily. Oh, you meant ZO. That is way more complicated than what you said, I guess. I couldn't hear all of what you said. So what is ZI going to be quickly? Just tell me that. If you connect a source here, how much resistance is the source going to see? What does the source see on this side? This part, remember, is disconnected as far as the AC current is concerned. There is no connection here. So what does VS see? Just this part. So what resistance does it see?
RG.
RG. So that's simple. The input impedance is still RG. Okay? So there's nothing, no difference there. Now let's come to the voltage gain, let's say. Now what is the output voltage? VO. This current is GMVGS, right? It's flowing through the RS, it's also flowing to RD. So when you want the drain to source voltage, you just take something which is connected between the drain to ground voltage, that's the output, not the drain to source voltage. You want drain to ground voltage, just take something which is a path between the drain and the ground and try to find the voltage drop through that. There, now you can see okay, remember this RD is not in the circuit. I'm assuming RD is too big. So I'm simplifying the thing. I've simplified the thing. Now, there are two different paths which take you from the drain to the ground. One is this one. But can you directly find out what is the voltage drop when you go from the drain to the ground along this path? Can you find that out? Yes? Come on. When you take a path, this is SCB's connection, right? How do you find the voltage drop across SCB's connection?
Sir, RS, GM, VGS.
That's where how much is the voltage drop? You have to be careful. GMVGS is a current. Okay?
There should
And
be
this
a
is a
voltage
current
drop
source.
due to current source also.
Yeah, you need the voltage drop across RS, and to that you need to add the voltage drop across the current source. The problem is you have no way of knowing how much the voltage drop across the current source will be a priori, because the current source can drop any amount of voltage and still give the same current, especially when it's an ideal current source, like in our example. Okay, so this path, in principle, you will get the voltage at the between the drain and the ground by adding this voltage drop and this voltage drop. But it's not very useful for us because we do not know what is the voltage drop across this. But the other one, that's easy. How much is the voltage drop across this?
Minus GM
Yes?
VGS
How much is
minus GM
GMVGS is the current?
times RD.
Yeah, and there's a minus sign because of the current's direction. Remember, this is how the current is flowing. So when you want VDS, which is a drop from the drain to the, sorry, not VO, Not VDS. I'm sorry. I keep on referring that to that as VDS, but that's not the VDS. That's the voltage at the drain, VD. VD is VO here, because drain, you want the voltage between the drain and the ground. That's VO. Fine, this is okay. But we need VO by VI for the voltage gain, right? So we need to relate VGS to VI. Once again, VGS is VG minus VS. How much is VG? This voltage? How much is it?
VI.
It's exactly VI. It's directly connected to the input, so it's VI. But how much is VS? VS is not 0, as was the case in the previous example. How much is VS? VS is the voltage here. How much is that? That's straightforward, right? You know
Minus
current
GM
through
VGS times RS.
It's just minus GM VGS times RS. Not this minus sign is simply this minus sign. VS is GM VGS into RS. A current of GM VGS flowing through RS produces a drop of GM VGS into RS. So that's the relationship between VGS and VI, but you have to essentially bring this to the other side. So VGS is VI divided by 1 plus GMRS. Okay? And so VO by VI, that's pretty easy to figure out. You just plug in the VGS value here and then divide by VI. You get minus GM. Again, the minus sign signifying the fact that the two are out of phase. This, of course, is an approximation because you have ignored small rd, but it's a very decent approximation usually. And also, if GM is large, GM is very large, then you can easily approximate this further for GM very big by RD. Now, when GM is very big, how do you find the limit? You just divide the numerator and the denominator by GM. Then this becomes 1 by RS plus 1 by GM. And if GM is very big, 1 by GM is very small. The denominator just becomes RS. Now, can anybody tell me from this result why we would want to keep some RS unbypassed? Remember, if we had bypassed the entire RS, this would have been just, this GMRS would have been 0. So the answer would have been minus GMRD. Okay, by the way, the answer we had was minus GM small rd parallel with capital RD. But within the approximation that we have done, which is small rd is very huge, this is what you would get, minus GMRD. Okay, that's when RS is 0. That is, the entire source resistance has been bypassed. But if you have not bypassed it, in the other limit for very large GM, you get minus RD by RS. Can anybody tell me why we would sometimes want to do this? It's obvious that this is less than GMRD, right? There's a 1 plus GMRS is bigger than 1. You're deliberately decreasing the gain by leaving RS unbypassed. Why would anybody want to do that?
Sir, am I audible?
Yeah, you're audible. Tell me.
So, because the gain is now the fraction between RD and RS, so it is
right.
independent of any
What?
changes.
Sorry,
Right?
to what? Sorry, I couldn't hear after you say fraction of RD and RS.
So, what I mean is that the gain is stable.
Could you just repeat that once again? I guess you're saying the right thing, but I couldn't hear you properly. What do you mean was?
I mean was the gain is stable.
Great. That's exactly the right answer. The point is GMRD, the gain without minus GMRD, the gain, forget the minus sign for the time being, the minus sign just gives you the phase. Size of the gain is GMRD without the RS, with the RS bypassed. But that may be much larger, it will be much larger than RD by RS. Okay. However, this one will depend strongly on GM, which is a FET parameter. Now, a FET, like the BJT, is an active device. And for active devices, the parameters are rather fickle. They change for various reasons, including drifting on the bias. As you have just seen, GM depends on the bias point, including temperature changes, including aging or replacing the FET by another FET. GMRD will be very, very fickle to those changes. You will get a large gain, but the gain will be rather unstable, will change from case to case for various reasons. On the other hand, if you leave some RS unbypassed, then for a very large GM, your result is minus RD by RS. Now there's a ratio between two resistances. Resistances are passive components. They are much more stable compared to the FET. They change much less. And in fact, if you make RD and RS out of the same material, then even temperature changes will not matter because RD and RS are going to change in proportion. Right? Is it okay? Clear? So what will happen is the gain now will be very stable compared to the previous gain. So very often in electronic circuits, I've said this several times, but this is so important that it has to be stressed. When you are talking about an amplifier, you very often think of getting a huge gain is what is great. That's really not the case. Getting a stable gain, a gain which you can control, is more important. So because you want to control the gain, very often you leave RS, at least part of RS unbypassed. If you left the entire RS unbypassed, you would get a large denominator that would bring down the gain a lot. If you leave part of the thing unbypassed, then you can still get a reasonably large gain, smaller than what you would have without the RS, but still a reasonably large gain, which is much more stable compared to the gain that your unbypassed or that your bypassed RS would have given you, okay, or the fixed bias circuit would have given you. So there are reasons why you may sometimes want to sacrifice the gain to at least get some more stability. Okay, homework, calculate Z0 for this circuit. Here, if you want to calculate Z0 for this circuit, don't get into the calculation very fast because you cannot really see RD in parallel with RS or small rd here. So you have RD, you have RS here, but you also have a GM VGS. So you have to do some calculation to get Z0. And for Z0, it's best not to just try to do it by inspection, but actually connect a VX and an IX. And now, the critical thing is, what you're making 0 is not VGS. What you're making 0 is VI for this calculation, for the Z0 calculation. But VI is not VGS in this circuit. That you have to bear in mind. Right? So making VI 0 makes VG 0. Does not make GM VGS go away. That is what you have to remember. Okay? Is that clear? Why doesn't it make GM VGS go away? Because VGS is VG minus VS, and VS is not 0 when VI is 0, because this current flows through the source resistance. Okay? So your homework is to calculate Z0. Also, and this is a bit more complicated, not very much more, if you take the small rd into account, then try to calculate these parameters once again. Try to calculate, say, AV. ZI is still RG, no complications there. But try to calculate AV and Z0, taking into account a finite small RD, not an infinite small RD that we have done here. So that's slightly more complicated. So two things that you have to do on your own. Calculate ZO for the self-biased circuit, and also with unbypassed RS, because with bypassed RS is the same calculation as before, as for the fixed bias circuit, that is. And then take into account the FET's own impedance, the drain resistance, and then repeat the calculation for AV and ZI and ZO. ZI, you don't have to repeat, it gives you the same result. So that's your homework. Okay. So this is a homework, this is an assignment which will be an actual assignment. Remember, by the way, I've already put up a problem sheet which you don't have to submit. I won't mind if somebody wants to submit it, but you don't have to submit it. Okay. The last one, there is a problem sheet which was due in the morning, but that's not the one I'm referring to. There's another problem sheet that was put up, problem sheet 9, which has no due date simply because you don't have to submit that. It's for practice.
Sir?
Okay. Now, unfortunately, I don't have to. Yeah, go ahead.
Sir, in PS8, there was a question like you did discussed where we didn't bypass the RS. So was
Sorry, I can't hear you clearly. And I'm running out of time today, so we will discuss that on Thursday. Okay?
okay, sir. Okay, sir.
Yeah. And why don't you just ask the question in the discussion forum so that I also know what question you are asking. That sort of doesn't catch me completely unawares. Sometimes it might happen that you ask me a question immediately here. I may not have an answer. Okay. Bye for today.